Welcome back to our discussion of general equilibrium. Last time we talked about Le Chatelier's principle and the concept and how it's going to predict for us what's going to happen. If that does not ring a bell, you need to go back a video and watch the previous one. Because what we're going to do now is actually to work out numerically a Le Chatelier's kind of topic with our particular reaction here and these particular numbers here. So let's look at what we've got going on. In a 1 liter vessel, we have hydrogen and iodine forming hydrogen iodide. That must all be gases, but it doesn't matter because we have concentrations at equilibrium. So am I going to use a K or a Q? I'm definitely going to use a K because I'm told at equilibrium. Now after this reaction here has reached these numbers and it's sitting at equilibrium, someone comes along and spills in 0.30 more moles of HI. Now check out, we'll come back to this, but that's moles, that's not molarity. So we want to know what the new equilibrium concentrations will be. Okay, when it gets back to equilibrium, what are the new concentrations? Well, first we have to figure out the number for K, because again, if we don't change temperature, the K number is the same, and that's the key to this particular problem, is we're changing something that does not change the value of Kc. So Kc equals concentration of products, which is HI, divided by concentration of reactants. Okay, before I move on, what should I do? Yes, it's worth that 30 seconds to be sure that your coefficients of your balanced chemical equation are in your formula. Oh, look at that, it was not. Good for me that I checked it. Okay, yeah, I did that on purpose, but you get the idea. Take that extra time to double check. Now we plug in our equilibrium amounts. So my equilibrium amounts is 0.490, and then 0.080 and 0.060. So 0.490 squared, because I still have that squared, 0.080 molarity, 0.060 molarity. I really should have had a molarity on that one too. There we go. Okay, so now, yay, calculator time, woohoo. I know it's that time you live for every day. When can I wake up and use my calculator to solve some chemistry? Yes, that is a joke. I know you don't do that. Okay. I get a number, and let's just round this to 50. That's not the appropriate amount of significant digits. We really should call that 50, point or 5.0 times 10 to the 1 would be better. But 50 is going to work for our purposes because that's not our final answer. That's just us trying to figure things out. Okay, so what do we know so far? We were at equilibrium, and that equilibrium had a Kc of 50. Now we're adding 0.300 more moles of HI. HI is a product. I'm adding more HI. So here's what I want to do. I want to build a new Rice table. And then we're going to find Q because we really are sure we're not at equilibrium. Okay, so my new Rice table is going to start with my reaction. H2 plus I2 in equilibrium. I like leaving some room. HI, and there's a 2 there. Okay, I am now starting initially with the old equilibrium numbers. Okay, my old equilibrium numbers are going to be what? My old equilibrium numbers were 0.080 molarity, 0.060 molarity, and check this out. I'm going to have the old equilibrium number of 0.49, that's supposed to be 90 molarity, plus what did I just add? Okay, I have to go back a couple slides. You have the convenience of looking up on paper. I've added 0.3 more moles of HI. I've added 0.300 more moles of HI in a 1 liter vessel. Because what must go into our Rice tables? moles or molarity, and since I've already started in molarity, I need to keep it in molarity. If I'd started into moles, I don't know why you'd want to in this case, but you could. You could convert everything to moles, and then you'd just work in moles. But working all the same. So how many moles in, oh look, that works out really well. They do that often on the test. Please read, please read the AP Chem test questions carefully so you can catch things like when they say you're in a 1 liter vessel, you're like, oh, I have this many moles in 1 liter, that's a molarity. Because they do that to make the math mentally easier, since you don't have a calculator on the free response. So 0.300 molarity. I'm going to get a grand total, if you don't mind, of 0.790 molarity. All right. I'm going to have some change. Here's the thing. And I added more products. Am I going to lose reactants to still make more products? Am I going to lose products to make some more reactants? Now, if you know Le Chatelier's principle, it would easily tell you, hey, I'm going to lose some products and I'm going to make more reactants. And check it out. I'm actually going to lose in a ratio of 2 to 1 to 1 because those ratios are important and they're still there. But that's jumping ahead of ourselves. That's using Le Chatelier's. Do you see why Le Chatelier's is so nice? Let's do it without Le Chatelier's. Let's find a Q. So Q equals concentration of HI squared divided by concentration of H2 and concentration of I2. My new total is 0.790 molarity squared. Same old 0.080 molarity and 0.060 molarity there. Sorry. And again, super fun calculator time. Woohoo. 0.79 squared divided by 0.08 divided by 0.06. 130. Q is 130. K was 50. How do they compare? Q is definitely greater than K. Which way does that reaction have to go to get back to K? To the left. I hope you see how that all works together to get you where you're needing to be. Now again, check it out. I already said that with Le Chatelier's. I didn't have to do this calculation, but they could ask you to prove with a calculation. They would literally write those words, prove with a calculation, and this would be your proof. Okay? But if they don't say those words, you can just say, according to Le Chatelier's principle, I need to use up some of this to make some of that to get back to equilibrium. So what do I have at equilibrium? Well, I have 0.080 plus X molarity. And I have 0.060, let's keep it consistent, minus X, no, sorry, plus X molarity. And over here I have 0.790 minus 2X molarity. I wanted the parenthesis there. Okay. Now we have our equilibrium concentrations with X's, but they don't want X's. They want us to do the math. So I'm going to transfer what we knew for equilibrium to this new slide because I am running out of room. So we had 0.080 minus X molarity. We had plus X. You got to stop me when I make mistakes like that. Yes, that is a joke. I know you can't stop me because you're on the other side of the video. 0.790 minus 2X molarity. Okay? So, we're going to get back to equilibrium. That means back to the original K worth 50. How are we going to get back to that? We're going to have concentration of HI squared equals concentration of H2 times concentration of I2, which means I'm going to have 0.790 minus 2X squared divided by that didn't work, 0.080 plus X and divided by 0.060 plus X. and we're going to set all of that equal to 50. Do you see where I'm going with that? Okay. Now, it is very unfortunate that we can't take any shortcuts. It'd be a lot more convenient if these were the same number. We could then square root both sides like we've done in the past, sort of a thing. Okay. It is going to work out where we're going to need a quadratic equation. But from here on out, it's just algebra. Okay, this is all equal to 50. So you do your FOIL here. You square this. You should know how to square something like that. Okay, and then you group your like terms. And you really do work it out to where you get something x squared plus or minus, I don't know how it's going to be, something x plus or minus something equal to 0. And then you have your a term, your b term, your c term. You plug it into your quadratic equation, and boom, there you go. That's a lot of algebra work, which is why they don't ask it on the test. I do ask of it on your homework because you can pull out your phone and Google quadratic equation solver, or you can pull out a calculator and actually just do it on the calculator. But on the test, I find that very unlikely. What I would expect on the test is they would have the same number here and here. So then you could have written that didn't work. You could have written it as a squared as well, and then square rooted both sides, and that would algebraically make things a lot simpler to solve. That is the way I would recommend that. But check it out. We can actually now figure out the new equilibrium concentrations. What did we have to do to get there? We had to, if we go the correct way, we had to first calculate what K was, because that was not given to us. They might even give that to us, but it wasn't in this case. I had no K with my original equilibrium, so we had to calculate it. Then I added in, well, this is not going the right direction. Then I added in the new additional amount. And we used both the calculation and Le Chatelier's to predict which way that would go. It's going to go from right to left. It's going to go in the reverse. It's going to shift to the left. We only need one of the two ways to prove it. But if you're sitting here going, I don't know what Le Chatelier's tells me, then you got to calculate it, because you guaranteed can't mess up the calculation in terms of is it going to be bigger than or less than K. Now maybe you can in the calculator mess up the calculation, but this would guarantee give it to you. Le Chatelier's, if you catch it, will do it a lot faster. That's the great thing about Le Chatelier's. Then I get my new equilibrium concentrations, and I solve for my new equilibrium concentrations. And in this time, we need a fun, happy algebra skills and quadratic equation. And isn't that so exciting? So I'm going to let you do this algebraically, because again, it really doesn't prove chemistry any more than this, but I do expect it on the homework. So if you are not familiar with how to do the quadratic equation, you better be sure you ask in class. Did this question, when you first read it, sound like it was going to be hard? Probably. Is it necessarily hard? No. It is simply applying everything you've learned so far. Will it take you a while? Yes, and that's why they have such things as long questions and short questions on the test. They're referring to the amount of time you would be spending on them, not the degree of hardness or easiness. That has nothing to do with it. I would still rank this as a relatively easy question. There was lots of steps though, so it is definitely considered a long question. Okay, I'm going to stop there, and then we'll get back to our final video next time over general equilibrium, just some few random thoughts to wrap up. Definitely, we're going to be practicing lots of K calculations. K before you do messes with equilibrium, K's after you do it, how K's compare with Q. This is what general equilibrium is all about. Either calculating K or Q, or using your K and Q to calculate the concentrations of everything else at equilibrium. So good luck with your practice.